Good day. My name is Jim Doolittle, and I'm a research soil scientist with the Natural Resource Conservation Service. I would like to talk with you today about some of the uses of ground penetrating radar in soil surveys and soil investigations. To start with, what is a soil survey? A soil survey is a field investigation of the soils in a specific area. Soil surveys identify the different kinds of soils, show their distribution on soil maps, and provide accompanying information and tables that describes and provide interpretations on soils and soil properties. Today, the results of soil surveys, that is, soil information, maps, and interpretations, are available online through the Web Soil Survey. The flexibility of the Web Soil Survey facilitates the updating of soil information by the Soil Science Division of NRCS and allows users to more easily access the most up-to-date soil information and also to customize that data to meet their specific needs. The Web Soil Survey provides users with access to one of the largest natural resource information systems in the world. To improve the information in the Web Soil Survey, soil scientists continue to go into the field to observe soils. They are equipped with the latest technologies for recording soil data, such as GPS receivers and tablet computers, which are loaded with the latest digital soil information and maps, aerial photographs, and LiDAR. In addition, soil samples are collected at selected points in the soil landscape and sent to a national laboratory for analysis and characterization. It has been said that it is easier to observe features in the deepest reaches of space than in the soil that is directly under our feet. The truth of this statement may lie in the observation tools that are used. The tools used in soil surveys have not changed very much over the last 100 years. The basic field tools of a soil scientist remain the humble spade and auger. These tools are slow, labor-intensive, and limited in the depth of observation. Characterizing soil spatial variability at field scales is a major challenge facing soil surveys and soil investigations. Soil data are largely collected with an auger and spade or with a mechanical probe at various points in a landscape. This point sampling method provides high-resolution data, but data collection is time-consuming, expensive, and generally confined to a limited number of sampling points. The inability of present field methods to adequately characterize soil among widely scattered observation points has fostered uncertainty in soil maps, interpretations, and models. At field scales, additional tools and methods are needed in soil exploration. To be effective, these methods must be relatively fast, accurate, inexpensive, and capable of characterizing the variability of soils at field scales. Because of its speed, economy, ease of use, and resolution of subsurface features, ground-penetrating radar offers significant advantages for the characterization of soil spatial variability at field scales. The effectiveness of GPR is highly soil-specific. Soils having high electrical conductivity rapidly attenuate radar energy, restrict penetration depths, and limit the effectiveness of GPR for a number of applications. The electrical conductivity of soils increases with increases in water, clay, and soluble salt contents. On this map, areas colored in shades of green are considered well suited to GPR soil investigations. Soils in these areas are dominantly coarse textured and have low soluble salt contents. Areas on this map colored in shades of brown and purple are considered poorly suited and unsuited to GPR soil investigations, respectively. The low suitability of these soils is a result of their high clay or soluble salt contents. The dots on this map show the location of NRCS's 17 radar operators. As you can see, there is a preference for areas that are shown in shades of green and have a high potential for the use of ground-penetrating radar. Different GPR systems and operating platforms are being used by soil scientists involved in soil investigations. Within the Soil Survey program, GPR is principally used as a quality control tool to determine the presence, depth, and lateral extent of diagnostic subsurface horizon, improve interpretation by providing estimates of different soil types composing mapped units, and characterizing the spatial and temporal variability of soil properties. As a quality control tool in soil surveys, GPR must provide a depth of observation of 2 meters or to a limiting or restricting soil layer, high resolution of subsurface features, and reasonable confidence in interpretations. Let's look at a few examples of the use of GPR in soil surveys. Here we see a soil profile and a radar record from an area of Pomona soil in Florida. 2 diagnostic subsurface horizons that are used in soil classification are evident on this image. A higher lying spodic and a deeper lying argillic horizon. As you can see, these horizons are highly variable in depth over short distances. The presence and depth to these 2 horizons affect soil classification and soil interpretation. Knowing this information is valuable to soil survey. Differences in parent material and particle sizes affect the soil classification and interpretation. Here we see a profile on our radar record from soils that have formed in a silty mantle of variable thickness over coarser texture glacial outwash. Differences in the depth to this discontinuity not only affect the classification of these soils, but their use and management. Here we see a profile and a radar record of a soil with a fragipan. On the radar record, the upper boundary of the fragipan has been highlighted with a white segmented line. Fragipans are subsurface layers that have a high bulk density and are very dense when dry. These layers are root and water restricting. In this example, GPR was used not only to identify the presence and depth to a fragipan, but to infer differences in its expression and consistency. In the investigation of organic soils, ground-penetrating radar has been used to determine the thickness and volume of peat deposits, classify organic soils based on soil depth criteria, assess internal features such as buried tree roots and mineral soil layers, and to characterize the structure, stratigraphy, and morphology of peatlands. As evident on this radar record, the organic mineral interface provides a strongly contrasting boundary that produces high amplitude reflections. NRCS soil scientists have used ground-penetrating radar to assess the relative concentration and distribution of features in soils such as roots, rock fragments, animal burrows, and yes, even unexploded ordnance and bodies. As an example, the presence, depth, and relative amount of plinthite in soil profiles is used to distinguish areas of Dothan soils, shown here, from other soils on similar landscapes in the southern Piedmont of the United States. Plinthite is an iron-rich, humus-poor mixture of clay with quartz and other minerals. Plinthite irreversibly hardens upon exposure to repeated wetting and drying, and therefore restricts water movement and the penetration of roots. On the soil profile below a depth of 90 centimeters, the darker colored bodies are plinthite nodules. Point reflectors occur throughout the radar record, but are most numerous between depths of 90 to 160 centimeters. Within this depth interval, most of the point reflectors represent plinthite nodules, which vary spatially in amounts. In this example, variations in the amplitude of these reflectors were used to infer the relative size and degree of induration of these nodules. Ironstone is an in situ concentration of iron oxide that is at least weakly cemented. Where continuous, ironstone can form root and water restricting layers, as shown on the images on the left. On the soil profile and radar records to the right, the ironstone is more irregular and discontinuous. GPR has been used to assess the relative concentration of these discontinuities or breaks in ironstone layers. In many upland areas, it is difficult to examine soils and determine the depth to bedrock with conventional soil survey tools. Rock fragments limit the effectiveness of these tools. One of the most effective uses of GPR has been to chart bedrock depths and determine the taxonomic composition of soil map units based on soil depth criteria. An example of the use of GPR to assess bedrock depths is the Montevallo Soil Study in Pennsylvania. The Montevallo Soil Series was established in Talladega County, Alabama in 1907 and is extensively mapped, as shown on this map, in Georgia, Tennessee, and Alabama. Montevallo soil was also mapped in one Pennsylvania county, Carbon County. Carbon County is located some 420 miles north of the northernmost county in Tennessee in which Montevallo soils are mapped. When mapped in Carbon County in the early 1960s, the Montevallo soil was classified as a shallow lithosoil. The classification and description of Montevallo soils changed over the ensuing years. In this study, ground-penetrating radar was used to confirm the depth to bedrock in areas that had been mapped as Montevallo soils in Carbon County. A strong correlation was found between the observed or measured depth to bedrock and the radar-interpreted depth. Based on a very large GPR database, the soil depth distribution is about 33% shallow, 60% moderately deep, and 7% deep in areas that are presently mapped as shallow Montevallo soils in Carbon counties. Areas presently mapped as shallow Montevallo soils will be changed to moderately deep Burke soil as a result of this study. Urban soils are difficult to map as a result of repeated and divergent land uses, the effect of land filling, land leveling, and surface removal, and the presence of heterogeneous fill materials with sharp and often broken transition caused by human activities. As a consequence, soils and soil properties vary greatly over short distances and do not conform to predictable soil-landscape relationships. Soil mapping is also made difficult because of the large number of auger refusals caused by excessive amounts of buried artifacts. The use of GPR and other geophysical methods are presently being explored to remotely sense and map anthropogenic soils in 3 major urban areas. Recently, GPR was used to investigate a portion of Liberty State Park in New Jersey. Here, GPR provided an estimate of the thickness of relatively clean fill materials that overlied older cold ash slag and dredged materials. It is anticipated that the use of GPR will expand in the study of anthropogenic soils. Many see the mapping of subaqueous soils as a new frontier of soil surveys. Subaqueous soils are soils formed in sediments found in shallow, permanently flooded environments. Excluded from this definition are areas permanently covered by waters that are too deep for the growth of rooted plants. In New England, several freshwater ponds and lakes have been mapped by collecting detailed bathymetric data using ground-penetrating radar systems operated in summer months from boats and in winter months from tracked vehicles. Based on radar data, the distribution of different subaqueous soils have been mapped. Recently, GPR was used to determine the bathymetry and to identify different radar facies in subaqueous soil landscape units beneath the U.S. portion of Missisquoi Bay in northwestern Vermont. A radar facies is a mappable, three-dimensional structural unit consisting of GPR reflections whose patterns and signal characteristics differ from those of adjoining units. Here we see 4 different radar facies that were identified on Missisquoi Bay. Using radar facies analysis, targeted sampling of the underlying sediments led to the identification of several distinct soil parent materials and subaqueous soil types. Differences in substrate and subaqueous landscape units were identified based on GPR data. The Google Earth image on the left shows the location of radar traverse lines in the interpretive bathymetry. The images on the right are two-dimensional, top, and three-dimensional, bottom, simulations of Missisquoi Bay, which were derived from the GPR data. These simulations show the depth, topography, and identified radar facies. With the near completion of soil surveys in the United States, ground-penetrating radar is being used increasingly to support technical soil services that help people better understand soils and soil information. As part of technical soil services, GPR is being used in the planning of resource conservation practices and resource management systems. As an example of the use of ground-penetrating radar in technical soil services, in New Jersey, working with Rutgers University, an NRCS radar operator charted a shallow compacted layer in a horse paddock. The radar record on the left shows a subsurface interface that was associated with the top of a compacted layer. Depths to this interface range from about 15 to 35 centimeters. Shallower depths to this compacted layer corresponded with the feeding area where the horses congregated. Heavily compacted soils are a concern to management as they have reduced rates of water infiltration and drainage and result in poor soil health. Field office staffs in several Wisconsin counties recently reported higher productivity and observed greater depths to bedrock than listed in the Web Soil Survey for areas mapped as Dunbarton soils. When these counties were originally mapped, it is likely that the observation depths were limited by a rubble layer which overlies the bedrock in areas of Dunbarton soils. As a technical soil survey project, GPR provided large, georeferenced data sets that helped overcome issues of data insufficiency and incorrectness and validated the deeper reported depths to bedrock. Ground-penetrating radar data was used to support changes in soil survey legends and interpretive data. Working with geologists in Minnesota, ground-penetrating radar was used to identify potential sinkholes and to assess the structural integrity of an emergency spillway to an earthen dam structure. Here we see a diagram showing the locations of the radar traverses and a potential solution cavity in the underlying limestone bedrock. In Florida, an NRCS radar operator working with the Southwest Florida Water Management District used GPR to conduct a wetland investigation in an area of Bassinger soils. As evident on this radar record, ground-penetrating radar was used to determine the depth to bedrock, identify solution cavities, and differences in the degree of karstification beneath this wetland area. In this study, ground-penetrating radar provided the spatial information needed by wetland managers. In Oregon, a wetland restoration project will remove a levee and thereby reconnect a river with a portion of its historic slough basin floodplain. Concerns have arisen concerning the possible loss of surface waters entering the slough basin to deeper aquifers. Ground-penetrating radar provided high-resolution data characterizing the underlying stratigraphy and depth to basalt. In this study, ground-penetrating radar was used to increase the sampling density, extend the information gathered from deep core measurements, and to expand the knowledge of the stratigraphy and depth to basaltic rock across the basin area. In Maine, the Natural Resource Conservation Service provides financial and technical assistance to the Environmental Quality Incentive Program, or the EQIP program, to agricultural producers for the creation of surface water irrigation reservoirs that are designed to conserve ground and surface waters. Depth to bedrock is a major factor in excavation cost, available volume, and the integrity of these structures. Soil scientists in Maine use ground-penetrating radar to map the depth to bedrock and assess the suitability of sites for irrigation storage reservoirs. Here is a representative radar record from one of those sites. On this radar record, The shallower and deeper interfaces represent the contact with firmer till and the solid rock, respectively. NRCS soil scientists have also conducted archaeological studies using ground-penetrating radar. These studies have deepened NRCS's partnership with various groups and demonstrated the agency's commitment to the identification, assessment, preservation, and protection of our nation's cultural resources in compliance with the National Historic Preservation Act. The use of GPR in soils and agriculture started in Florida over 35 years ago. A firm foundation in soil survey and a pathway in agriculture has been established. Today, younger minds are using a host of complementary technologies and exploring new areas of application for GPR in soils and agriculture. These younger, more innovative minds are finding new ways to process, archive, and display radar data, especially in GIS. I am confident that in the future, GPR will have an expanded role to play in both soils and agriculture. I thank you. Good day.